As you approach the speed of light, normal mechanical quantities begin to take on a different form. If length and time depend on the inertial reference frame in which they are in, then that must mean that anything derived from length or time can be relativistic as well. Momentum is another relativistic quantity that is modified when objects move at very high speeds. Consider two balls on a pool table traveling parallel to, but on opposite sides of, a chalk line down the middle of the pool table. The two balls are traveling at the same speed towards each other parallel to the line. This means that their paths are also parallel to each other, so there is no y component to either of their velocities. They are traveling close enough to that line that they will hit in the middle with a blow which will cause them to glance off of each other and travel off in a slightly different direction. If you recall the conservation of momentum, then you know that we can conclude that after the collision they will have equal and opposite small velocities in the y direction, and the x direction velocities will have decreased very slightly from their original velocity. Now let's say that instead of balls on a pool table, we have two rockets moving towards each other in the same fashion. They are moving parallel to some imaginary string in space, far from any gravitational fields that might affect them. They are traveling at the same speed in a way that they will just glance off of each other when they meet. Again, each object moves away from the other with a y velocity that is equal and opposite to the other. But now imagine you are inside one of the spaceships. You have been looking out the window and watched the string go by with a very high velocity. After the collision, you can watch the string move away from you at some velocity, say, 15 meters per second. This is your spaceship's new y velocity that acts perpendicular to the string. At the same time, a person in the other spaceship observes the same thing. Since the situation is symmetrical, she also sees the string moving away from her ship at a velocity of 15 meters per second. Since both of our spaceships are traveling at a high velocity, the big question becomes how fast do you see the other spaceship moving away from the string? Well, first off, remember that length contraction only occurs in the direction of motion. So if the person in the other spaceship observes her ship moving away from the string for 15 meters, you would agree that her ship has indeed moved 15 meters. Also, according to her, the 15-meter distance would be occurring over the course of 1 second. However, since you are traveling at a high velocity, time dilation would cause you to observe the 15 meters to happen over the course of more than 1 second. So as a result of time dilation, the collision as viewed from your spaceship does not cause equal and opposite velocities for each spaceship in the y direction. Now, way back when, we defined momentum as the mass times the velocity. So in the case of our spaceships, we have some object of mass m moving at some very high velocity v. We also kind of implied that the conservation laws of physics must be adhered to at all times, and even Einstein never wavered from this concept. It was up to him then to explain how to conserve momentum at high velocities. To do this, he came up with a hypothesis that said the mass of an object must depend on its speed. So an object at rest has some mass, m sub 0, which is sometimes referred to as the rest mass. And if that object begins to move at relativistic velocities, then it will have an inertia that is equal to its relativistic mass. This relativistic mass is simply the rest mass times the Lorentz factor. We have seen this expression for gamma a few times now. This Lorentz factor is 1 over the square root of 1 minus the velocity squared divided by the speed of light squared. Note that this relativistic mass increase is in an undetectably small effect at ordinary speeds. So the everyday situations that surround you, the relativistic mass is the same as the rest mass. But again, as an object approaches the speed of light, the mass increases without limit. So if we were looking at momentum at relativistic speeds, then we need to account for that in our momentum equation. Instead of using the rest mass in our momentum calculations, we would use the relativistic mass. For an object moving at a speed close to the speed of light, the momentum can be expressed as the relativistic mass times the velocity times the Lorentz factor. Another way to reconcile the idea of relativistic mass is to understand that all forms of energy have an inertia. That is to say that kinetic energy itself has inertia. I know, blame Einstein, but think about that for a second. Inertia is one of the two defining properties of mass, along with how that mass attracts other mass gravitationally. So if we increase the kinetic energy of a body, it will increase the relativistic mass, which will, in turn, increase the gravitational field around it. In a nice ordinary non-relativistic situation, the kinetic energy of a particle is equal to 1/2 the mass times the velocity squared. In order to put ordinary objects in motion, we must do some work on them. In other words, we need to apply some force over some distance. So applying some force will cause mass to accelerate and can be expressed as kinetic energy. Another way we can say that is the force we apply causes some rate of change of momentum. Now, if we are moving close to the speed of light, if we keep applying a force, the velocity really isn't going to be changing a whole lot. Instead, the mass is going to be increasing. Since momentum is the mass times the velocity, we can say that the force is equal to the rate of change of the mass times the velocity, which in this case is the speed of light. So there is some force being applied to a particle of mass, m, that is traveling pretty close to the speed of light. As we continue to apply the force, the speed can't really increase, so the mass increases. So the work done, instead of increasing the velocity of the particle, goes into increasing the mass. We can write this in more of a shorthand notion as F equals mc, where F is the force, m is the rate of change in mass, and c is the speed of light. Note that m is not the total mass of the particle, but the rate that the mass changes. And since it is a rate, we can define the time it takes to do this as 1 second. So m is the change in mass in a 1 second time period. Now back to our kinetic energy. Remember, it is just the work done, which is some force acting over a distance. And we just define the force as the change in mass times c. But even better, since we have defined our time period as 1 second, we can use the speed of light as a way to determine the distance that the force acts over as equal to 3 times 10 to the 8th meters, which we can just refer to as c meters. Put that back into our expression, we get the relationship between an increase in mass of a relativistic particle and its increase in kinetic energy to be E equals mc squared. So here we have Einstein's famous equation that mathematically relates a particle's energy and mass. However, for this to apply in reality, then mass ought to be able to be converted into other forms of energy and vice versa. And actually, since Einstein has suggested this, there have been many situations in nuclear and elementary particle physics that have experimentally supported this. For example, when an electron and a positron collide, both particles will disappear and electromagnetic radiation will be produced. Amazingly, the amount of energy produced is exactly equal to that predicted by the E equals mc squared. We can see the reverse process in our own sun, as its mass is continually decreasing as it emits electromagnetic radiation. Even more interestingly, this equation is now thought to apply to all processes. Obviously, most things are moving far slower than the speed of light, and therefore the changes produced are much too small to actually measure. But when the energy of any system changes, the mass of the system changes by this predicted amount.